I've got my marker. Review. Okay, we're gonna take them pretty much in order in the beginning. Number one, the force between two bodies that have identical electric charges. That could be either two pluses or two negatives. Always going to be repulsion. Yeah. So that would be A. Two, atoms having equal or nearly equal electronegativities are expected to form what kind of bonds? Covalent? Yes, that's true. E is true, but is there a better one? Non-polar covalent. C. Yeah. Non-polar covalent. If they're almost equal in electronegativities, they're definitely going to be non-polar. 3. Well, the elements cesium, fluorine, and chlorine. Cesium, fluorine, and chlorine. The order of increasing electronegativity. All right, we look at the position on the periodic table for these guys. Like this, like that, that. And then we have a couple of down here. Don't even figure into it. Cesium is way down here. Chlorine is up here, and fluorine is up there. Helium's there, and hydrogen's there. So lower left to upper right, this one should be, and it says from increasing. So, oops, that's not exactly correct. Less than chlorine, less than fluorine. Cesium, chlorine, and fluorine in that order would be increasing electronegativity. The electron pair in the carbon-fluorine bond could be considered. All right, so if we got fluorine, and then carbon is about here. So when you form that bond, you're going to have, let's see, that's 4. You're going to have, just looking at that bond, it's going to be polar in this direction. So which one fits that? The electron pair closer to fluorine because fluorine has a higher electronegativity than carbon. That's B. And when we say the pair is closer to fluorine, what we mean is the distribution of electron density in this bond. And if you look at the whole possibility for the bond, it's like that with most of the density in here. We don't say that the pair, I mean, we imply that the pair is exactly between them, but you know, it's not really, because Heisenberg's uncertainty says we can't know exactly where those electrons are because we're more interested in their energy than we are in their position. So we focus on the energy and let the position be more like a regional description. But in terms of probable location, they're more likely to be closer to fluorine than they are to carbon. That's all we're saying. Number 5, let's see, let me clear the board. Except for that drawing, I think I'll leave that there in case we need it again. Which of the following molecules has no dipole moment? All right. What do we need? What are the 2 things we need to predict the dipole moment for a molecule? 1, bond polarity. And 2, geometry. Okay. So if we look at those 3 molecules, CO2, ammonia, and water, we would have to, the bonds are going to be between carbon and oxygen. Now that's not accurate, but it's just showing you the polarity of the bonds are going to be there. There's going to be polar toward the oxygens. These are going to be polar toward the nitrogen. And these are going to be polar toward the oxygen. We've drawn these often enough, we probably shouldn't even have to do if you don't remember, then do the Lewis dot structure procedure. Find out that this is double bond here. When you have a central atom with two groups around it, that's always linear. In this case, it's linear electronic geometry because there are no lone pairs. It's also molecular geometry. So even though the bonds are polar this way and that way, they're equal and opposite to each other, so they cancel each other out. This is non-polar. Whereas with ammonia, we have this trigonal pyramid as a geometry, and the bonds being polar this way and this way, they add up to a polarity that way. That's called vector addition. And of course, water is, we know it's polar that way. So these two are polar, CO2 is non-polar. So all of them, two of them have polar, so D can't be it and E can't be it either, because carbon dioxide is non-polar, has no dipole moment. All right. Take a look at 6. Which of the following has the smallest radius? All right. We didn't spend a lot of time on ionic radii. I did mention one thing about ionic radii. When you have the atom and it becomes negatively charged, the radius is going to increase because we add another electron out there. And if you remove an electron, it's going to shrink. And usually when you do that, you're either adding to the next principal quantum number, right, the next valence level, or you're subtracting from that valence level and shrinking down to the next lowest one. So you're definitely changing the radius when you add or subtract electrons. All right, so if we put, let's see. Let's look at the atomic radius first. So potassium is going to be, let's see, down about here, okay, in the third period, right? Oh, fourth period. Then the third here, second there. Now, second needs to be moved a little higher. Third, second, and first. There we go. Then chlorine. I think chlorine is over here. And about, yeah, right about here. There. Rubidium. Rubidium is down here, below potassium. Okay. And sulfur is in the third period below oxygen. So if this is fluorine, this would be sulfur next to chlorine. And the last one, argon. Argon is over here. Okay. So we know that this is going to be atomic speaking, right? Neutral atoms. It's going to be biggest, next, then they shrink this way. So it'd be next largest, then smaller, and then the smallest would be this would be the order for atomic. Let's see. Like that. Okay. And when we turn them into ions like that, that's not, there's no ion there. Minus there, 2 minus, minus 1. We're adding electrons to these guys. So it effectively makes this one as big as that one. Well, not exactly, because it doesn't have enough protons in it. So it's going to be more like one of these over here. So adding electrons to these guys puts them into the 4th valence shell. So it makes them huge compared to or comparable to these. All right. So sulfur, chlorine, and argon. Fluorine's the smallest. What it said, smallest radius. Okay, smallest radius. So if we subtract an electron from this one, and potassium has 19 protons, it has more protons than these. Plus, we've removed an electron. So it's going to shrink it to a size smaller than these guys. It's going to like move up here. And fluorine, we've added an electron, so it's over here, but it's only got 9 protons. Right, so it's still going to be out like that. The smallest one then is going to be potassium. And rubidium's not smaller because it's moving up into this region by losing an electron. Right, and that one moved up here. So best way I can explain it is these guys ballooned, these guys shrunk, but that one didn't shrink enough. Right, this one shrunk the most because it has the most number of protons compared to these guys. This one has more protons still, but they're in the 4th. It does have some shielding. I know that's not a very good explanation, but it's the best I can do. So this is the smallest radius, potassium. The only way to verify that is actually get the data, get the hard numbers and compare them. We're trying to rationalize it at this point. Now, as if that wasn't bad enough, now we're going to try to put some in order. Which of the following arrangements is in order of decreasing size? Okay, let's see what we've got. Gallium, calcium, potassium, chlorine, sulfur. Okay, A and B have the same ions in them. It looks like they all have the same ions in them. So we have gallium 3+, which is under, so in the 4th period below boron. Right here, this is gallium. Okay. And calcium is over here. All right, we have potassium there too. Yes, potassium's right next door. Kind of busy in here. Go. And then we have chlorine, which is up here, right about there. And we also have sulfur. Yes, we have sulfur right next door to it. Right here. Okay. So what I like to do is nail down the ends. Like what's the biggest and what's the smallest? The biggest one is going to be sulfur. Right? Because the trend is, for atomic speaking, is decrease in size this way. But we've added 2 electrons in the 4th level in order to, well, actually we added 2 electrons in the 3rd level. but there are fewer protons. That's the key here. So this one should be the largest. And the smallest would be in this fourth level, gallium has 31 protons. And if we remove 3 electrons, then it's got no fourth period, it's got no fourth level electrons left, but it's still got those 31 protons. So it's going to shrink it way down. That means gallium should be the smallest. 3 plus. There we go. Smallest. Right. So then if we go in and then put them in order, then chlorine should be the next smallest. I think. Yeah. Because we removed an electron from that one. And then what do we have left? We have potassium and calcium. So which one of these is calcium should be smaller than potassium, right? Because we removed. I think that's the way it should go. And well, it agrees with the key. This is one of the more difficult types of problems to try to figure out, to rationally approach ionic size. Number 8. That must have been number 7. That was 7. I didn't write the number up. So for those watching in TV land, that was number 7. In the reaction between magnesium and sulfur, magnesium atoms become anions, cations, part of a polyatomic, share electrons with sulfur, crystallize. All right, what happens to a metal usually in a chemical reaction with a nonmetal? It loses electrons. Metals love to lose electrons. Nonmetals like to gain electrons. So that makes the metal a cation. Magnesium becomes a cation. Choose the molecule with the strongest bond. Okay, we've got the diatomics halogens here. Right, we've got fluorine, chlorine, bromine, and iodine. Is that it? Yeah. They're not all equal. How do we assess the strength of the bond? These are going to be nonpolar covalent, for sure. And the strength of a bond is related to the overlap of orbitals. Right? The orbitals that overlap, the valence orbitals for these are getting bigger. So the bigger the orbital and the farther away the orbitals are, like the valence orbitals for iodine are going to be 5. So this is principal number, quantum number 5, 4, 3, 2. So you get larger orbitals having to overlap, and they can't overlap as well because they're so big. If you get close enough to overlap more, then you start getting into the repulsion problem, where the protons repel and the electrons repel. So there's a limit to the overlap that you can accomplish with these big ones. So this is going to be the weakest. So if we're talking about, did it say which is the strongest? Okay, the weakest one is this one. And then bromine is a little bit stronger because you can get closer. And chlorine is stronger yet. But here's the kicker. Fluorine cannot get as close, the nuclei can't get as close as chlorines can, because the nuclei are getting too close. There's a trade-off. When you get these nuclei close enough that you would expect the fluorine to be the strongest bond, it doesn't happen. So in fact, what happens is fluorine is the next strongest and chlorine is the strongest. Because you get the maximum overlap without repulsion. You can't get the fluorine atoms close enough to overcome that advantage. Okay. So that's, I guess you'd call that an anomaly. We would expect it to go, from biggest to smallest and forget about it. But the data tells us that dichlorine has the strongest bond. And they're all single bonds, right? So we're not comparing apples and oranges. All right. We skipped a few. Let's see. We need to look at those Roman numeral 1 through 5 for number 12. Draw the Lewis structures for the molecules below and use them to answer the following questions. All right. 12 says these molecules have a 0 net dipole moment. So like we did before, are the bonds polar? And what's their geometry? That's what we have to look at. So 1 through 5. I think I'm going to erase this now. I'll redraw it if I have to. So Roman numeral 1, 2, give yourself plenty of room. All right, so we got boron, trihydride, NO2, SF6, and ozone, and phosphorus pentachloride. Okay, so we know how to draw the Lewis dot structures, right? Boron has 3 valence electrons and 1 each for the hydrogen gives us 6 total. I'm going to do the valence electrons first and then go back. Nitrogen has 5 and 2 times 6 is 12, so it's 17 electrons for that. Fluorine is a halogen, so it has 6 times 7 is 42, plus sulfur, which has 6. 6 and 42 is 48. Okay. 3 times 6 is 18. Phosphorus has 5, I believe. 5, and 5 times 7 is 35, so that's 40. 40 valence electrons. Okay. Now we can put them together. We have boron in the middle, and the hydrogen's like that. 2, 4, 6, we're done. Right. Boron is deficient, but it exists. That compound does exist, so we're stuck with it. What's the geometry of this one? 3 pairs around the central atom. Trigonal planar. What does that say about well, if there is polarity, it doesn't matter which direction it is because they're all equal, pointed to the apexes of an equilateral triangle. So they all cancel each other out anyway. I mean, we could speculate on what the polarity of the bonds is, but it doesn't matter because they cancel out. NO2. So we have N and an O and an O. So that's minus 4 is 13, right? 2, 4, 6, 8, 10, 12. So that means we have 1 electron left over, and it has to go on that nitrogen. Now, the problem, see, here's the problem with theories. the localized electron model for this valence bond theory doesn't work very well for this compound. This compound does exist. Now, did I do it right? Like nitrogen is 5, yeah. 2 times 6, 12, 17. So we got the right number of electrons. It just, when we draw them out, now we've got that unpaired electron, which makes it what? A free radical. Unpaired electrons means free radicals. So it should be extremely reactive. All right, so we can make a double bond and get closer to an octet, but we're not going to get there. All right, we could put it on either side. And we could do that one, we could do the other one, and then resonate them. But what does that mean for our geometry? Well, the electronic geometry is going to be trigonal planar. But the molecular geometry is going to be bent, which means we do have a dipole. Okay. How about SF6? Well, let's see, sulfur and 6 fluorines. 1, 2, 3, 4, 5, 6. 6 times 2 is 12, which is equal to 36 left over, right? 2, 4, 6. We have 6 times 6 is 36. If we put 6 around each of the fluorines to make an octet, then we've used up all of our electrons. Right. So what's the geometry here? The electronic and molecular be the same because there are no lone pairs. Not around the central atom. This is octahedral. And the polarity is definitely toward the fluorine. But they're all perfectly balanced. And we have a nonpolar molecule. Go back to the questions. 0 net dipole. Okay. So we found one. We found a second one. Ozone. So O. Which oxygen goes in the middle? Trick question. Take your pick. When you just O3, doesn't matter. So we have -4 is 14. 2, 4, 6, 8, 10, 12, 14. And we want to make an octet. So we could either take it from this side or from the other side. For our purposes, it doesn't matter which one. So we've got 3 around that central atom. We have a trigonal planar electronic geometry. But a bent molecular geometry. Now, why did I go to all that trouble? Well, this one should not have a dipole because they're all oxygens. But if we draw it like this, I'll leave out these lone pairs. Lone pair up here, that should give us a partial dipole toward that lone pair. So this should be polar, slightly, because it has that extra lone pair up here. So I'm not going to include that one in the nonpolar set. Now, does that run contrary to the answer? No. Okay. So I made the correct assumption, I think. And PCl5. Right. We have phosphorus in the middle. 1, 2, 3, 4, 5 chlorines. 2, 4, 6, 8, 10. That means we have 30 left over. 2, 4, 6. 6 times 5 is 30. All of them used up. No lone pairs around the central atom. So the electronic geometry and the molecular geometry would be the same. 5 groups around the central atom is what structure? A trigonal bipyramid. We would say like this, there, that. phosphorus in the middle, and we have chlorine up here, chlorine here, chlorine there, chlorine in the back, and a chlorine there. They're all balanced. The polarity in each bond is toward the chlorine, but they're perfectly balanced in this regular geometry. So this one is also nonpolar. 1, 3, and 5, which would be B. Okay. This was the tricky one right here. Because normally you would say if the bonds are not polar, the molecule's not polar. But when you got those lone pairs in there, they influence the polarity of the molecule. I think that's why I put that problem in there. Well, they created it, but I picked it because for that reason. 13. That took a lot of time. Oops. Manage this one.
The best way to look at the problem is see that 5 is on all of them and 3 is on all of them. And you just have to prove between the first or the fourth. And see.
Yeah. Yeah, you could save yourself some time there. Sure. If I were a student instead of an instructor, that's probably what I'd do. Okay, 13. How many electrons must be shown as bonding or non-bonding in the Lewis structure whose skeleton is this? How many electrons must be shown? Okay, we've got 4 carbons and an oxygen, right? And then we've got these 3 have hydrogens, and then we have 3 on the end. Okay, those are hydrogens. Okay, how many electrons must be in the Lewis structure? Well, carbon has 4. 1, 2, 3, 4, that's 16. 1, 2, 3, 4, 5, 6 for the hydrogens and 6 for the oxygen. Right. So that's 28, right? 28 electrons. That was easy. Oh, we go ahead while we got that one up there. I know it's not marked, but let's go ahead and do 14. This is an organic molecule. 28 electrons. 28 electrons. And we've counted for 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 8 electrons. And we start on the outside, work in. Hydrogens can't take anymore. So we have 8 electrons. Put there, 2, 4, 6. We have 2 electrons left over. All right, where do they go? Well, we've got an octet here. We can easily make an octet here by just moving a pair there. So those other 2 electrons are best put over on these 2 somewhere. The reason for that is if you put the 2 electrons, if you're strictly following the rules and you put 6 here and then 2 here, then this one already has an octet. That's an octet, and these guys have nothing. So if we move those 2 electrons over here to one of these carbons, now they can move in here like that. And that gives this an octet, octet, and that's an octet. I think that's why I wanted to do this, because it's kind of tricky. So between 2 and 3, how many electrons are shared? Well, if this is 2 and that's 3, 2, 4 electrons. 2 pair, 4 electrons. Right. Yeah. Except before I step on. 16. In the Lewis structure for ICl2 minus, how many lone pair electrons are around the central iodine atom? ICl2 minus. Remember, whenever we have a charge, we have to count that as an electron in the group. So 3 times 7 is 21 plus 1 is 22 electrons. Okay. We're looking for lone pair. So iodine is going to be in the middle. When you have a situation like this, you go for the one that's more metallic than the others. They're not metals, but more metallic means either to the left or below. So iodine goes in the middle. Okay, that's 4. 18 electrons. 2, 4, 6, 8, 10, 12. So we have 6. 2, 4, 6. Or 3 pair. Lone pair electrons. 3. Let's see, 19. How many resonance structures can be drawn for the molecule O3? All right, we looked at O3 before. O, let's see. Yeah, 18 minus 4 was 14. 2, 4, 6, 8, 10, 12, 14. There we go. So you can either form a double bond on this side, or you can do the same thing only on this side. And resonate these 2 structures. So there are really only 2 structures that can be drawn for ozone within the confines of the localized electron model. All right, number 28. Which of the following types of molecules always has a dipole moment? All right, A through E. All right, A, linear molecules with 2 identical bonds. That's always nonpolar. Not always polar, it's always nonpolar. Well, yeah, if it's linear, that's true. Tetrahedral, 4 identical bonds. That's always nonpolar. Like carbon tetrachloride or methane, be good examples. Trigonal pyramid molecules, 3 identical bonds. The trigonal pyramid, how do you get a trigonal pyramid? That's not one of our regular structures. You get a trigonal pyramid, ammonia is the best example. Right? You got a hydrogen in the back, got hydrogens out here. They form that base. Okay, and then you have a lone pair up there. The trigonal pyramid is formed like that. Now these molecules will always be polar. And the reason for that is that it's a tetrahedral electronic structure, but the trigonal pyramid, you cover that lone pair, and that lone pair gives it polarity. So ammonia is a polar molecule, or anything like it. This is always polar. We found our answer, didn't we? Yeah. If we went to D, E can't be it because we found one. Trigonal planar molecules, no, trigonal planars are always, they cancel each other out. They're not polar. So we found our answer. And let's see. 21. Which set listed our increasing electronegativity? All right, we got some that are similar and some that are different. And they kind of mix it up, don't they? All right, here's what I'm going to do. Fluorine, nitrogen, carbon, silicon. Fluorine, nitrogen. Yeah. Carbon, silicon. Phosphorus added from B. Nitrogen, oxygen, chlorine, fluorine, silicon, sulfur. Oxygen, sulfur, chlorine, oxygen. Okay, did I get all the elements in there? I think I did. Increasing electronegativity. All right, so the least electronegative is below and to the left, which would be silicon, sulfur, oxygen, carbon. Yeah, silicon would be the least electronegative of those. The most electronegative, obviously, would be fluorine. And then, if we stay in the same period, fluorine left oxygen, and then nitrogen, and then carbon. Let's see, let me mark them as we get them here. Oxygen. And then we move down, sulfur should be next. And then phosphorus. Okay, so if we put those in the correct order and we look for ones that match in the correct order, well, we can throw A and E out. Fluorine's on the wrong side, right? B, C, and D has fluorine okay. D has silicon okay, but the sulfur and oxygen are flipped, right? No, sulfur and oxygen are correct. So why isn't it D? It says B, phosphorus, nitrogen, oxygen, fluorine. Silicon, sulfur, oxygen, fluorine. Oh, we got two choices. It could be B or D, couldn't it? Yeah. Okay. B or D. Now, no, silicon's in the non-metal group. It's a metalloid. Increasing electronegativity. Now, that's our reasoning. Now, if we went and actually looked at the values, maybe that would break the tie. That's my guess. It would probably break the tie for B if we looked at the true electronegativity values. But with what we're given, right, B and D are tied. Yeah. Never noticed that before. If something like that shows up on an exam, you know, and it has the same discrepancy, you know, call me on it. Because you ought to get credit for your answer if you pick the other one. 22. Which choice has bonds listed in order of increasing bond energy? All right. The first one is hydrogen-halogen bonds. Now, in this case, the closer you can get that hydrogen to the nucleus, the stronger the bond. Only A is reversed. It ought to be, HF should be the strongest bond, then HCl, and then HBr the weakest. So those carets ought to go the other direction for A. All right, so A can't be it. It's not the correct order. Single, double, triple bond. That's a good one. Right. Increasing order. We've already talked about C. The chlorine and the fluorine are out of order. So it can't be C. And then D. The carbon-carbon bond in C2H4 is a double bond. And nitrogen is a triple bond. Oops. Right. So that disqualifies D right there. The other way around. This one should be stronger than that one. And we found our answer. 23. In the gaseous phase, which of the following diatomic molecules would be the most polar? All right, let's see. 23 is it? Yeah. A, B, C, D, and E. All right. Cesium fluoride, cesium chloride, sodium chloride. You know what? I think this is a lot easier than I'm making it out. The most polar bond of all of them would be the ones with the electronegativities with the greatest difference. Cesium's way down in the lower left-hand corner, fluorine's in the upper right-hand corner. That's why I think cesium fluoride would have the most polar bond. It may not be the strongest, but it will be the most polar. In fact, as you increase polarity, you weaken the bond because you're pulling electrons preferentially to one side more in a very polar bond than you would in a slightly polar bond. And that weakens the bond. So the answer is A. Cesium fluoride should be the most polar. 25. Which of the following ionic compounds has the largest lattice energy? Lattice energy most favorable to a stable lattice. All right, when we say the largest lattice energy, that is when those gas ions come together and make that solid, the greatest, the most negative, delta H for that, give up that energy, is the most stable. So two things affect the lattice energy. One is the size of the charge difference. Like if it's just single charges, or if it's double charge right here, like that, that would be a greater attraction, give up more energy. And charge density, which means smaller ions. So if you can make this one smaller and concentrate the charge, then you can increase that lattice energy. Two things are working there. So what we have to go on here is E. Yeah, E. We have barium oxide, beryllium oxide, cesium iodide, sodium bromide, and barium sulfide. Okay, let's look at charge difference. Barium and beryllium are both alkaline earths. 2, 2, 2 minus, 2 minus. Cesium is an alkaline metal, plus and minus. Plus, minus, 2 plus, 2 minus. So if we eliminate the ones with not enough charge, then we throw these out. Then we look at the size of the ions. Sulfur is going to be a much bigger ion than oxygen. So it diffuses that charge over more volume, right? Lower charge density. Similar, and barium. So this one would have a stronger bond than that one. Right, so we can eliminate that one in favor of that one. Then we can compare these two. Right? These oxygen ions are going to be the same size, but the positive charged ion is going to be more dense in charge for beryllium because it's smaller. So beryllium oxide is your strongest lattice energy. Okay. 26. First electron affinity value for oxygen is blank, and the second affinity value is, unfavorable versus favorable. Favorable is implied from exothermic. And one of the reasons for that is if you look at the progress of a reaction versus energy of its components. If you look at exothermic, right, you're going to have reactants up here. And you got your activation energy, and then you come down here like that. Have we done that before? We haven't looked at that yet, second semester. Okay, you're getting a preview. The amount of energy required for this reaction to go, the activation energy, is right here. That amount of energy, you have to rise to that point before you can go to products. And this is exothermic because the products have less energy than the reactants. It gives up those energy. You feel it as heat or light or something else, but it gives up energy. But if you go backwards, the endothermic direction, you have to add energy to get there. The activation energy now is between that and that. So this activation energy is much higher than that one. That's why this one, the forward direction is favorable and the reverse direction is not favorable. Okay. All right. So with that in mind, the first electron affinity value for oxygen, remember how we write electron affinity? This is a gas neutral atom. It picks up an electron and makes a gas with a 1- charge. That's the first electron affinity. So it's going to give up some energy because that oxygen is looking for another electron. It has 8 protons. It's going to pick up that electron. This is neutral. And it has 2 orbitals that are not occupied. Right. It's 2p. It has 2p. 1, 2, 3. Like that. Let's see. 1, 2, 2, 3, 4. Like that. So it's got room for another electron. We put an electron in here. I'm going to do that just to distinguish what we're looking at. Okay, so that should be exothermic, favorable. Okay, now if you do the second affinity, you've got a negatively charged. This is 1, this is 2, and you're going to make that one. Okay. The problem here, even though we've got a place for it, is that this thing is already negatively charged and it repels that electron. This is unfavorable. This is exothermic. This is endothermic. So that makes this one favorable, that one unfavorable, which would be D. Now the question is, why does oxygen prefer a 2- charge? Because it does. I mean, we got to explain why it does. Well, looking at this is favorable. So it gives up a certain amount of energy. This delta H is negative. This delta H is positive. So what we're looking for is the delta H total to be negative. We want that to be negative, to be favorable overall. So that means that when we put this one together with, let's see, this is 1, 1, and 2. Together with this one, positive, this one has to exceed the absolute value of that one in order to make the overall negative. So the favorability of the first electron affinity must exceed the value of the unfavorability of the second one in order to make it overall favorable. That's the easiest explanation for this. Now that wasn't part of the question, but I thought I'd throw it in for free. We'll dig into this in more detail. Let's see. About the 3rd chapter, I think, of next semester, when we get into kinetics. All right. Let's see, 27. Using the following reaction data, calculate the energy of HF bond. Okay. All right. The energy of the HF bond is the lattice energy. The reason for that is, let's see, HF. The reason for that is H would be like that, fluorine would be like that, and we would produce this. You know, actually that doesn't work because you normally think of lattice energy as producing a solid. But I think it should work like that. So the energy of that, so this, if we're using Hess's law, that's what we're after right there. So how do we get there? No, my mistake. We're not looking at lattice energy. We're looking at this equation right here. This free atom coming together with this free atom as a gas to form that one. That would be our target equation. Now, how do we get there? Well, let's see. If we use Hess, we need HF on this side. So that first equation, H2 plus F2 yields 2HF, would give us HF like that, like that. And I'm going to throw in the correction factor here in a second. H2, yes. We only need one of them. That equation has 2 of them. We only need one, so that means we need a half of this one and a half of that one. And the value for delta H should be half of a minus 542. Divided by 2, delta H. Okay, so that gets this part. Now we want, let's see, H on this side. We've got H2 yields 2H, but we need to flip it. All right, so we need H on this side. And we've got, actually, I'm going to write it the way it's given first. H2, that. What we need is half of that. But the sign has to be reversed. Right? 432 minus 432 because we flipped the equation. But now we want to do half. So I'm going to say that and that. And we do the same thing for fluorine. I'm sure that equation is in there also. Change the sign. Minus 154 divided by 2, because we took half of it. Minus 154 divided by 2. Correct? Now, does that get us where we want to be? Right. H on this side, F on this side, HF on this side. Yep, 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 yep. And this one cancels that one. This one cancels that one. And we're covered, right? So I just need, when I put it in my calculator, I got to remember to take half of these, half of each one. I can just add them all together and then take half. How about that? 542, 432, 154. Change the sign, divide by 2. I got 564 minus 564 kilojoules. No, yeah. Okay. Calculate the energy of the bond. All right. This is the amount of energy that would be given up when the bond forms. Okay, I wrote it backwards. Right? Calculate the energy of the bond. When we talk about the energy of a bond, how much energy does it take to break the bond? So I wrote all these things backwards. You just take each one and flip it. And that makes these positive and makes that one positive. Fortunately, our choices don't have negatives in them. And by convention, bond energies are all positive because that's the amount of energy required to break the bond. They have to be positive. Okay. So I admit my mistake. All right, 28. All right. As indicated by the Lewis structure, which of the following would probably not exist as a stable molecule? All right. Let's see. A, B, C, D, E. Did we do formal charge yet? I think we did, didn't we? Calculate formal charge? Yeah, with Lewis structures. Okay. That's one approach to this molecule, this problem. The other is to draw the Lewis, well, it says as indicated by the Lewis structure. So we're going to draw the Lewis structure first anyway. So we got methanol. That's the kind you don't drink. CH2O, formaldehyde. CH3O, I don't have a clue. Right? If you know your chemistry, pick C right away. Because I've never seen that molecule before. This one I have. That looks like acetylene. And C3H4 would take some doing, but it's probably true. All right. So if this is 4 and 3 times 1 and 6 and then another 1. So we have 14 electrons. This will be 4 plus 6 is 10 plus 2 is 12. This would be 4 plus 3 is 7 and 6 is 13. And this would be 8, 9, 10. And this would be 3 times 4 is 12 plus 4 is 16. Okay. So the way organic molecules are written is the hydrogens that follow that carbon are all attached to the carbon. And the carbon is also attached to this next non-hydrogen, oxygen. So we would draw it like this, like that, and like that. 2, 4, 6, 8, 10. So now we have 4 electrons left. And they would go right here. And everybody's got an octet or a duet. That's a good molecule. CH2. So we have C, H, H, and O. So that's 6 electrons left. 2, 4, 6. Carbon doesn't have an octet yet. So do that. That's an aldehyde in organic chemistry. Carbon that's a carbonyl group. That's a good molecule. I'm gonna skip that one because we know that's the wrong one. If we draw this one, that 2, 4, 6, 8, 10. There you go. Then this one takes a little bit more work. Right? Okay, where do those hydrogens go? Typically, the hydrogens go on the outside if we need a place to put them. So that's 2, 4, 6, 8, 10, 12. We got 4 electrons left. If we put them here and here, then we can form a octet on this side with a double bond and an octet on this side with a double bond. That's a fairly stable molecule. It's symmetrical. Symmetry usually gives you the lowest formal charge. Now this one is not going to work. 1, 2, 3. That oxygen, 2, 4, 6, 8, 5 electrons left. 2, 4, 5. If it existed, it'd be a free radical because this is already an octet, but this one doesn't have an octet. Oxygen's got a septet. So that for that reason, this would probably not be a stable molecule if it ever existed. I think that was just an exercise in drawing Lewis dot structures. Right. 29. We're doing on time. Probably going to run out. Using these electronegative values, select from the following group molecules that fit the given statement. Okay. So down below, this molecule contains a carbon atom with a trigonal planar geometry. All right. We know Let's do the ones that we've done before and we know how they're gonna come out. This is none. We know carbon dioxide. We've done that one over and over and over again. That's linear. That's not trigonal planar. C2H6 is D. C2H6 is like that. Both of those carbons are tetrahedral. So you have 4 groups around each one. CH3Cl would be like that, and like that, I think. Let's see, 3, 7, 7 is 14. 2, 4, 6, 8, 10, 12, 14. Right. This would be tetrahedral. Now, did it specify around the carbon atom? Right, so that carbon atom is tetrahedral, linear. So by process of elimination, well, since it says none, we got to do the top one. CH3CHO. CH3CHO would be 2 carbons is 4 times 2 is 8, then plus 4 for the hydrogens, and then oxygen is 6. So that's 18 electrons. So we would have these hydrogens attached to that carbon, and this carbon would have a hydrogen and an oxygen. 2, 4, 6, 8, 10, 12. So we have 6 electrons left over. 2, 4, 6. Okay, this one's already got an octet. So we need to make an octet here. Just move it over like that. Okay, now, that's a tetrahedral carbon. This one has 3 groups. It's trigonal planar. So A would be the best answer. One of those carbons is trigonal planar. .34. Of the following, which molecule has the largest bond angle? Okay. Again, we can do the ones that we've already done before and save ourselves some time. E, more than one of the above has equally large bond angles. Okay. Well, what's the largest bond angle you can have in a molecule? Linear, 180 degrees, right? If you go over 180, then your bond angle's on the other side, and it's less than 180. So 180 is the tops. O3 is a bent molecule, right? So it's going to be 120 degrees for this one. Nominally, right? It's probably going to be less because of the lone pair electrons. HCN. Let's cut straight to the chase. We've drawn this one before. There you have 180 degrees. Oh, it says more than one. Okay. Water, nominally 109.5 tetrahedral, but it's less. It's probably 107, about 107. Okay, so how about B? If B is not linear, OF2, right? 6 plus 14 is 20 electrons. OF, F. So that's 4, 16. 2, 4, 6, 8, 10, 12, 14, 16. We got another bent molecule. Right? It's laid out like water. So this has the largest bond angle, and E can't be. Okay. 35. All right, which of the following molecules is non-polar overall? All right. C, D, E. A, SF4, SF2, carbon tetrachloride, H2S, and OCl2. H2S is like, right, sulfur is a chalcogen. It's like water. This is going to be a bent molecule, just like water. So it's polar. Carbon tetrachloride is tetrahedral. We've done that one before. This is nonpolar. Well, that's the answer. Because we don't have any wonky ones in there. Like two of the above, none of the above. But if we drew the others, right, this would be 28 plus 6 is 34. Sulfur with fluorine. So 2, 4, 6, 8, 26, and 6 times 4 is 24. All right, so we have 2 electrons left over. There we go. We got a lone pair in a trigonal planar, trigonal bipyramid. Right, 5 groups, trigonal bipyramid. And when we draw a trigonal bipyramid with a lone pair on it, where does the lone pair go? On the triangle. Right. So with these fluorines here, and back here, bond there, bond there, bond there, bond there. What we look like is a seesaw. Okay, but it's unbalanced. We have polar bonds that are unbalanced, so this one is polar. SF2 would be 6 plus 14 is 20. So SF4 is 16. 2, 4, 6, 8, 10, 12, 14, 16. We got a bent molecule, right, with polar bonds. This one is also polar. And OCl2, right, 6 plus 2 times 7 is 14, 20. OCl. I think we're going to end up like this one. Two, 4, 6, 8, 10, 12, 14, 16, 18, 20. Yep. So this one's bent also. And it's polar. The non-polar one is carbon tetrachloride. $36. Which of the 5 molecules are non-linear? NO2 minus C2H2 N3 minus and HCN. We know that one's linear. We know this one's linear. And H2O2. So we've done this one before. This one is linear. This one is linear. This is acetylene. It's linear. So now we just have to do the others. The question was non-linear, right? We did this one before too, didn't we? 5 plus 12 is 17, 18. Yeah, 18 electrons. O. 4 is 14. 2, 4, 6, 8, 10, 12. Well, maybe we didn't do this one. You don't want to like it. So that puts all our electrons in there. Now we need an octet. So we can either do it from this side or the other side. 2, 4, 6, 8. And this is a bent molecule. So it has a dipole. And this one is 16 electrons. N. Oh. Got my charge. Let's see. 4 would be 12 electrons left over. 2, 4, 6, 8, 10, 12. Okay. Now we want to make an octet. So to balance it, we put a double bond on this side and a double bond on that side. And okay. It looks like that one's linear. I drew it correctly. And H2O2. I'll go ahead and do this one for you. That's bent here and bent there. So this is has a dipole. So back to the question. Nonlinear. H2O2 and NO2 minus. C. Okay. N3 minus, I think. That's the azide ion. Yeah, that's the azide ion. They used to use that as sodium azide in airbags, car airbags. But for various reasons, they got away from that. And they've had several different concoctions that can produce lots of gas very quickly. But you need something that's stable over a long period of time and will not spontaneously ignite. It waits for the charge from your accelerometer in the car to tell you that you're stopping too quick. So bag blows up. All right. And 38. Molecular structure of BRF6 plus. RF6 plus. Okay. We've got 7 halogens. 7 times 7 is 49. But we lost an electron. So we only have 48. Okay. And bromine is more metallic than fluorine. It goes in the middle. 1, 2, 3, 4, 5, 6. Two, 4, 6, 8, 10, 12. So that's 36. 2, 4, 6. 6 times 6 is 36. So we got no lone pairs around that bromine. They're all occupied around the fluorines. So what structure do we have with 6 groups? Octahedral. Octahedral. That would be C. All right. 39. Okay. Molecular structure for xenon oxyfluoride. Okay. This has 8, this has 6, and 2 times 7 is 14. So that's 28. Xenon will go in the center. Whenever you make a compound with a noble gas, it always goes in the center. So we got that, we got a fluorine and an oxygen. And so that's 6, 22. 2, 4, 6, 8, 10, 12, 15, 16, 18. And that's 4, right? 2, 4. Okay. So the electronic structure is 1, 2, 3, 4, 5. A trigonal bipyramid. Xenon in the middle. Got say we'll put an oxygen down here. Let's see. You know what? I think for balance sake, fluorine should go here and oxygen should go there. And the 2 lone pairs will be on the triangle as usual. Like that. Okay. So where are the bonds? Well, these bonds are drawn correctly, but this one needs a bond right here. So when you turn it on its side and look at it or turn it up, it doesn't matter. The molecule is T-shaped. That would be C.
Should it not be trigonal planar?
Trigonal planar? Oh, because you start with the electronic geometry first. And the electronic is trigonal bipyramid. Then you cover up the lone pairs, and what's left? A T. You can't go straight to the molecular geometry when you have lone pairs.
All right.
Let's see, 44. You shouldn't even have to do this one. 44, correct molecular structure for a silicon. Let's see. Yeah, 44. Notice where silicon's located. It's in the carbon group. So it's analogous to that compound, methane. Right? This is methane. Methane is tetrahedral with no lone pairs. This one is also tetrahedral. Why? Because this model uses valence electrons only. Silicon and oxygen have the same number of valence electrons, 6, with the same hydrogens around. I mean, we could draw it, but this is a good explanation too. And also, instead of saying, we don't say carbon tetrahydride, we don't say silicon tetrahydride. We use the organic nomenclature. This is methane. So that makes this one silane.
No worries.
Now you can prove that it's tetrahedral, just draw the dot structure. Right? And it'll take you there too. 46. Molecular structure for B, B, E, C, O. 2. Let's see, beryllium has 2. Yeah. 2 times 7 is 14. So that's 16 electrons. Beryllium in the middle. Fluorine, so that's minus 4. 12. 2, 4, 6, 8, 10, 12. Okay. In this case, we can make an octet for beryllium because we have available these lone pairs. So we can do, and the formal charge will be best accommodated by a balance. So we'll do like that. But the molecule is still linear. Okay. if those were hydrogens, then beryllium would just be stuck. It would be deficient. All right, 48. In the molecule xenon difluoride, how many pairs of electrons surround xenon and what's the molecular geometry? Okay, xenon difluoride. And it asks for how many pairs of electrons around xenon. You got 8 here, 2 times 7 is 14, that's 22 electrons. Xenon in the middle, fluorine, so that's 4, 18, yep. 2, 4, 6, 8, 10, 12, 14, 16, 18. 3 pair of electrons. Oh. And it's asking for molecular geometry. Okay. So 1, 2, 3, 4, 5. Trigonal bipyramid. And we're going to have this triangle with xenon in the middle, a fluorine up here, a fluorine down here, and all the lone pairs go on the triangle. So this is a linear molecule. All right, 3 lone pairs, linear molecular structure. All right, 49. Choose the member of each set that best matches the label. Okay, of those pairs, we got beryllium and barium. Which one is more metallic? The one with the lowest electronegativity is the most likely to give up electrons, which makes it more metallic. So the more metallic is the one down below, barium. Barium's the more metallic of that pair. The more covalent bond, well, you need 2, well, you need nonmetals. Magnesium and oxygen are metal nonmetal. That's not covalent. N2O, nitrous oxide, laughing gas. That's the more covalent. And the next one, highest electronegativity. All right. Lower left to upper right, increasing. So the one that's furthest up in the right-hand corner is oxygen. Right. Sulfur's below it, and bromine's below and to the right of that. So oxygen would be the highest electronegativity. Barium, nitrous oxide, and oxygen, which would be E. Right? I'm going to run out of time. I'm not going to eat up any of your lab time. So when it comes time for lab, 3:30. Right? 3:35. Or we could keep going until your partner shows up. Okay, we'll do that then. Use the bond energies given below to calculate the enthalpy change for the reaction. HCN, oh, let's see, 50. So we got HCN, gas, plus 2 hydrogens yields CH3 and H2. CH3 and H2. And we've done this, you have to know the structure in order to use this method. So this is going to be, that's going to be hydrogen cyanide. This is going to be hydrogen. And you got 2 of them. This one's going to have these 3 hydrogens there. Then we're going to have this one, hydrogen there, like that. It's kind of like ammonia, right? 3 bonds, 3 single bonds, and a lone pair. Okay. So now, and that's just one of those. Okay, now we can do it. You take the bond energies for the, let's see. Take the bond energies for the reactants, subtract the bond energies for products. Because when these bonds come together, they give up energy. We need to make those negative. And for these, we need to keep the values positive because they're used to break the bonds. That's why you do them in that order. This one minus that one. Because all those values are positive. Okay, a CH. CH is 413. There's just one of them. And these are in kilojoules. And then a CN triple bond. Go. 891. 891. Oh, sorry. And then we have 2 times a hydrogen bond, 432. Then we subtract 3 carbon hydrogens, 413. Plus a carbon nitrogen single bond, carbon nitrogen 305. And then a nitrogen, 2 nitrogen hydrogen bonds. 391. So you add all these up, change the sign, add all these up and put them together. And in the interest of time, we should end up with minus 158 kilojoules for that reaction. And it comes out pretty close. When you do the experiment and measure the value, compare it to the calculated value, they come very close to each other. It's amazing. All right. Let's see. 1, 2. All right. We got those. I'm going to have to leave those for you guys to. Oh, no, I got a few more minutes, don't I? Yeah. Sorry. Let's see. I was at 51. 51 and 52 are given together. They're the same type of problem. 51 actually gives you the reaction and the name of the reaction to use Hess's law to generate the target equation. So that first one from solid to gas is sublimation. The second one is the bond energy of H and Br. Right? The third one is ionization energy. We've seen that one before. Then electron affinity for the bromine. And then the lattice energy for the lithium ion bromine ion makes solid. And then the bond energy for 2 hydrogens. And it would take a lot of time to put that together. Let me see, did I do an adequate description in the worked problems? Let me see if it's worth leaving at that. Yeah, it looks okay. So in the interest of time, I'm going to leave 51 for leave 51 for you guys to do. Or you can look at a previous video. I want to go to 52 because it's essentially the same thing, only it's got abbreviations. And you have to know what those abbreviations mean and the reactions that are assigned to those abbreviations. So I think 52 would be more valuable to you guys. Calculate the lattice energy of rubidium chloride from the following data. So our target equation is rubidium and fluorine yields, is that right? Yeah. Rubidium is the alkali metal. Rubidium fluoride solid. We want the energy for that reaction. And what we have is, first of all, we have sublimation of rubidium. So let's put it over here. The sublimation of rubidium is solid to gas. That's sublimation energy, 85.8 kilojoules for that one. The next one is ionization energy, first ionization energy for rubidium. So how do you write that one? First ionization energy, you need rubidium gas yields rubidium ion plus an electron. And the amount of energy required is 397.5 kilojoules. Right? That's endothermic. Endothermic, endothermic. The second one is BE for Cl2. BE means bond energy. So bond energy is how much energy does it take to break this bond? So that means it has to be a gas and it has to produce 2 chlorine atoms in a gaseous state. That's what that means. 226 kilojoules. So these are all positive endothermics. The next one is enthalpy of formation for rubidium chloride. The enthalpy of formation, remember you start with the product. Rubidium chloride in its most stable form, a solid. And you form that from the neutral, well, actually the most stable forms for each of these. So rubidium would be a solid, right? It'd be a metal solid. But chlorine would be Cl2, gas. And we only need one of them, so we would say 1/2. That would be the expression for the heats of formation, minus 431. That's an exothermic process. And then the last one is, let's see, EA. Oh, electron affinity. Electron affinity for chlorine. So that would be Cl, gas, plus an electron yields Cl minus gas. And that should give up minus 332 kilojoules. That's what you have to do to set up to solve this equation. Okay? So let's start on this side. How do we get rubidium fluoride solid into that equation? Is that right? Rubidium fluoride. No, chloride. Why don't you guys stop me? There we go. Now it's making sense. Okay, this solid shows up where? Right here. So if we do that one, rubidium chloride solid, it's formed from rubidium solid plus 1/2 chlorine gas. And we wrote it exactly as it appears here. That's minus 431 kilojoules. Okay, did that one. And we covered that one. Okay, now we want to get this chlorine minus here. All right, that one has to be flipped to put the chloride ion on the correct side. So we've got to put the chloride ion here. And then put the chlorine gas plus the electron on this side. That means we have to change that sign, plus 332. Okay, that was covered. That was covered here. Now, how about rubidium plus? Rubidium plus here. Yep, there it is. It needs to be on this side. Gas, electron, and rubidium gas. Change the sign. Minus 397.5 kilojoules. Okay, takes care of that one. Now, we've got all of these guys accounted for, but now we've got, well, that cancels that. Do that one. These, and let's see, this one, and these. We've got to find a way to get rid of those. So rubidium, let's start from the top. We got to put rubidium solid on this side from one we haven't used yet. Here, right there. So that rubidium solid needs to go on this side. And this rubidium gas on this side. And we change the minus 85.8. So far, we haven't had to multiply or divide by a constant. And we've just used that one. And that takes out that one, rubidium. It takes out this one, like that. So what do we got left? Well, let's see, that one's underlined and this one's underlined. So we got to get chlorine gas on this side, right here. Oh, we've already used that, sorry. Here. So we need chlorine gas on that side to cancel this one. And we need Cl2 on this side. That one started out as 2, but we only need half of that much. So if we take half of the whole thing, and then since we flipped it, we change the sign. Let's see, where am I? Here? Yeah, here. Minus 226. But we took half of it. Right, so we divide by 2. Change the sign and divide by the same divisor for this. Okay, that takes care of, that's all of our equations. So we should have eliminated this one and this one. Right. So that one's gone, that one's gone. This one's kept for here. That one's gone. This one kept for here. That one's gone. These two are gone, leaves us with that. So if we did our math correctly, take half of this value, add that one, that one, that one, that one together. And you should get, if I did everything right, you should get minus 695. Minus 695 kilojoules. And what does that mean? That's the lattice energy. That's a lot of work. Looks like an extra credit. A bonus problem. And I think, oh, all right, I'm out of time. This is fairly straightforward. All right, put it in your own words. Beryllium chloride, why? In spite of the large electronegativity difference between beryllium chloride has no dipole, but sulfur dichloride does have a dipole. And it has to do with not just the polarity of the bonds, but the geometry of the molecule. Beryllium chloride is linear, so it cancels out, makes it a nonlinear nonpolar. Whereas sulfur dichloride is a bent molecule. It starts off with a tetrahedral electronic geometry, but it gives a bent form and a dipole. Lewis structure, shape of the molecule, and polarity. Right. If we draw this one, we get what electronic geometry? And don't forget that minus sign, right? The original ICL4 has a minus charge. So you got to keep the minus sign on the dot structure. That's an octahedral electronic geometry. In octahedrals, the lone pairs go on the apex. And the square in the middle keeps the atoms until you have to. If you have to use the square, then instead of 2 pair, you would have 3 pair or 4 pair or 5 pair. Right. But you start from the apexes first with your lone pairs. In this case, you only have 2 lone pairs. So that leaves the square in the middle with atoms on it. And that's square planar. That's left over from an octahedral electronic geometry. And it's nonpolar because all of those bonds are slightly polar, right? Because chlorine is more electronegative than iodine, right? But they cancel each other out. So this whole molecule is nonpolar and it's square planar. I think that's the last one. Yeah.